Gresham College presents Home Office Mathematics by Professor Bernard Silverman, FRS.
Well, I'm going to first of all talk a bit about Home Office science, because people say, well, what science is there in the Home Office? And you might be quite interested. And of course, the purpose of the Home Office is to look after us all. And I'm told that the original lectures were given in Latin as well as in English. And so that you can ponder the question, quis custodiet custodies ipsos, which means, I have to translate it, don't I? I went to school about 300 yards from here, and we learnt that, and it means who looks after the people who look after us. We've consolidated Home Office science into a single organisation under the leadership of the Chief Scientific Advisor. So I should explain that Home Office science is not just me, it's a reducing number, but about 300 people in different areas of science who work in the department which I head. And so I do two different things. One is to be a scientific advisor in my own right and give advice on particular topics which I either know about or keep a few pages ahead in the book, or know someone else who knows something. And also, of course, I manage a large group of really very talented people who it's a great privilege to work with. The main work of the Home Office is in three areas: crime, migration, and counter-terrorism. But we also include work on registration. We include the General Register Office, the issue of passports, the Government Equalities Office, and also one piece of my work is on the regulation of animal experiments. So you can see it's a very, very wide brief. Not as wide as it was in the 18th century when there were only two departments of state, I believe, the Northern Department and the Southern Department. The Northern Department dealt with things from here north, in other words, Britain, roughly speaking, and the Southern was abroad, everywhere else. So it's not quite as it was, but that's how it was originally. Science involved in all these areas: crime, migration, counterterrorism, and so on. In a day's work, I find myself involved in everything. It can move, you realize at the end of the day that you've been talking or dealing with scientific work in all of these different areas, possibly just reading something someone else has done, or trying to explain to the ministers why we should be doing a particular piece of work, or actually giving your own particular expertise. It's really interesting. And sometimes not all my input is specifically mathematical. It's often to do with biology, with social science, or with just the general principles of scientific method. But underneath it all, and of course mathematics is really like this, because frankly, all science is maths. That's it, really. It all often involves statistical or mathematical thinking. Our structure, we have a thing called the Centre for Applied Science and Technology, CAST. Like all good new managers, the first thing I did when I came in was rebrand the entire organisation. It used to be called something else. And it's about 150 people, a few more, based on two sites near the M25, one near St Albans and one near Horsham. And I'll tell you something about the work of CAST later. Then we have a secretariat which looks after our advisory committees and does things like help me if I have to appear before a parliamentary committee. We have Home Office Statistics, which produces statistics on various different areas. And we have teams of operational researchers, economists, social researchers, and so on, who support policy in the various areas. So that's an overview of the whole structure. Home Office statistics. So what I'm going to do is to give you a few vignettes of little pieces of work that we do, and it'll give you an idea, as I say, both of the scope of Home Office science, and on the way we'll do some mathematics. We compile statistics on all aspects of our activities, but we've recently transferred crime statistics to the Office of National Statistics. Now, the way crime statistics are collected is itself interesting, because there are two different sources of crime statistics. One is police-recorded crime, and the other is a thing called the British Crime Survey, shortly to be renamed the Crime Survey of England and Wales, because that's what it is. And the police-recorded crime is simple. you are the victim of a crime, you report it to the police, they clock it up on their computer, and then we publish the data. The British Crime Survey involves asking people if they have been the victims of crime, doing a survey. And it's a very interesting piece of work to collate these two, because, of course, it's not all crimes are reported to the police, and also the way that police report crimes isn't necessarily the way you think they do. In other words, because crimes have technical definitions, you might imagine that you've been a victim of one sort of crime when the police, according to their technical definition, define the crime in a different way. And so if I ask you what happened to you, you might say, well, I was a victim of burglary. Now, I'm actually not sure whether it still exists, and the police might have put that down as a different kind of theft. So that's the sort of thing I mean. And so there are, and the other thing is that the level of, not all crime is reported, and so the level of crime as measured by the police recorded crime is not the same as the level reported by the British Crime Survey. Government is, of course, most interested in whether crime is going up or down, and over the last 20 years, crime has generally gone down, but the government doesn't feel, and rightly so, that it's at a reasonable level. It still feels too high. But the real problems arise if the two statistics start going in opposite directions. And you can see it's very sensitive, and that's why, one of the reasons why the government's decided that it would be better for the Home Office not to collect these data at all, or not to publish them, but it to be done by the completely independent Office of National Statistics. And so that is what they've decided to do. But at the moment, we are still ourselves doing it. Most government statistics isn't statistics in a very mathematical sense, but it's a matter of carefully collecting and analysing data from various sources. And some of the work we do, we have to be rather clever about the way we do it, because it can be very, very expensive to collect the data directly, and it's often better to do something using some cunning administrative source. We use some other process that you're doing in order to collect the data. So police recorded crime, I guess, is of that kind. And so that's very interesting. The other thing we do is we do social and economic analysis to underpin policy and operations in all these areas, crime and security and migration. And although some of that is qualitative, involving small-scale, not even surveys, but talking to people and things like that, or some is straightforward quantitative work, as I've just said, some of it involves somewhat more sophisticated mathematics, particular statistical nature. And it's really to think of the cunning way of measuring something in the most cost-effective but still accurate way that we can. Now, I want to talk a bit about the Migration Advisory Committee. So this is the first of my little vignettes. This isn't actually under my purview, but it's part of the work that we do. And one of the things that's very interesting is to measure the economic impact of possible migration policies. And in order to do that, it's necessary to have an estimate of what's called displacement, which is this question: if a person comes to this country, do they displace someone who is already working here? So what's the reduction in employment of those already here caused by new immigrants into the country? And we have a thing called the Migration Advisory Committee, and that's one of our expert advisory committees. They've done some work on this. So this illustrates the way we use expert advisory committees, and also I'm going to explain what they actually did. And they're particularly concerned about the effect of migration from outside the European Union. So how did it work? Well, there are two possible answers to the question I just asked. So the first is what economists normally will tell you, and this is called the lump. This is about something called the lump of labour fallacy. And classic economic theory says that there's no fixed number of jobs, but employment rises to match any increase in labour force. So in other words, if you if there's 5% unemployment and a lot of people come to the country, there will still be 5% unemployment, and the number of jobs will grow, or maybe less. The number of jobs will grow to match the number of people coming into the country. Because the idea that the number of jobs is fixed is called the lump of labour fallacy. And I might say this applies equally to arguments about whether increasing the retirement age takes away jobs from younger workers. So the notion that that people, will have to work longer, and that's taking jobs away from younger people, is the lump of labour fallacy. And classic economics says that the lump of labour fallacy is a fallacy. In other words, if more people come into the country, it does not displace any existing workers. The popular conception is different. The popular conception is that the total number of jobs is indeed fixed, or more or less so. So if a worker comes in from abroad, it takes away a job from someone else. So someone else is out of work as a result. Or, for that matter, if someone stays in a job beyond retirement age, that, again, would have the same effect. But I want you to just see why that might not be so, because if someone is working, they spend money and they pay taxes and so on, and so that creates economic activity, which creates jobs for others, and that's why the economists say that this doesn't happen. The MAC decided they wanted to actually, the Home Secretary asked them to think about this and actually do some analytical work, and that's what I'm going to try and talk about. So they used an econometric approach, roughly as follows. So they took data for various regions of the country over several decades, about 30 years. And in every region and in every year, they found the demographic composition. So let's say native in this sense, I'm not sure it means native born, but it means completely settled. It may mean native born, but it doesn't actually make any difference because we're looking at changes, and you'll see, because we actually look at the way this composition changes. So if someone's in a particular group, it doesn't really matter where they are. It's how the numbers change in different groups that will make the difference. So we've got native, EU and non-EU, and the employment rates. And then they used a statistical multiple regression. What they then did was they took this demographic composition and they took the employment rates. And what economists then do is they difference everything. So they see how much did this ratio between these things change and how much the employment rate changed. That gives you, for every year and every region, you get essentially a few data points. And then you can construct a statistical model that says how do the changes in demography correlate with the changes in employment. And that's what they did, and they fitted a multiple regression model, and this was the answer. So the MAC analysis showed that neither of the two extremes, or the two things I said earlier, were true. So it was neither the case that if someone comes, it makes no difference to existing workers, nor was it the case that there's a complete displacement. Their data analysis shows, it's a very big, thick book, it's published, you can read it, that the displacement called for migration from outside the EU is in the short run about 23%, with a standard error of 5.5%. So it means it's somewhere between 10% and 30%, so it's not very accurately estimated. But what it means is, if it was 25%, it would mean that for every 4 migrants that came in, there would only be 3 jobs. So 1 existing worker would not be employed. And that is interesting, but they also found that after a few years the effect washes out, so after 5 years there's no discernible displacement effect. And this is an extremely important result for government policy because it shows, and it's contrary to the standard economic position, that there is indeed some displacement, and it quantifies it. And if I may say, it also kind of accords with common sense. It's sort of sensible too. It's rather nice when a bit of work like this actually comes up with something which sort of makes sense, because it does make sense that if a lot of people come in, it will have some depressing effect on the economy short term of the people already there, but in the long run it won't. And also that it's only 23%, that makes sense also. So that's quite interesting. And that makes a big difference to the way that the government's migration policies pan out in terms of their economic effect on the country. It demonstrates a big difference, and so it's been very important. I might say they did it for EU as well. I should just tell you what the EU result is. So the result for EU migration is that the displacement effect is 23%, but it's got such a big standard error that you can't say it isn't zero. And so you can't be sure it's not zero because the standard error at the conference was so large that it actually includes zero as a possibility. But, you know, so that, but in any case, you can't, that wasn't part of the main question. Animal experiments. Now, I feel very honoured to be here. In a minute, I'll explain why, because there's a point at which I'm going to sit down and ask someone else in the audience to give the rest of the talk. But anyway, part of my responsibility is to oversee the issue of licensing for experiments involving animals. And I hope you won't be offended if I quote, I'm not sure who it is, but some well-known scientist, I think it's Colin Blakemore, who said that there ought to be a notice in every doctor's surgery that said every medicine and every treatment recommended in this surgery has been tested on animals. And the reason is you wouldn't want to take something if it hadn't been tested to be safe and effective, and animal experimentation is part of that. So that's not government policy, that's just something. However, I have in my life seen some horrific and unnecessary animal experiments, I have to say. About 30, 40 years ago, I visited a place where they were trying to test cigarettes on, they had pigs that smoked in order to try and design less dangerous cigarettes. And this seems a completely immoral experiment for two reasons. First of all, you shouldn't do that sort of thing to pigs. And secondly, there are plenty of willing human subjects who will even pay for the privilege of taking part in this experiment. And by the way, about smoking, it shortens your life. It doubles your death rate at every age. There's some lovely statistical work done many years ago. So whatever your chance of dying in the next year is, if you smoke, it's double. So not a good idea. In my previous job as head of a college, I used to try to say this sort of to young people, and they just got very angry. Fortunately, I'm talking to mainly for people who will take it more seriously. So anyway. And so we've rightly arrived at an ethical view that we should be very, very careful about what experiments we do, and there's a detailed system of regulation. And part of that's based on the 3 R's, which are not reading, writing, arithmetic, but replacement, refinement, and reduction. And these have been for some years part of the government's policy, but they're underlined by the Coalition Agreement, which explicitly commits to working to reduce the use of animals, which is what, by the way, was going on anyway. So there's just 2 mathematical things I might talk about. So the first thing is the idea of replacement, which this is the notion of using methods other than live animals wherever possible. And as our understanding of both genomics and the way that drugs work improve, we can predict, to some extent at least, how a new compound will actually work. So you don't have to just blindly try it out, because you can already know, to a large extent, using mathematical models, lots of computer stuff around chemistry, biology, genomics, and so on, what the effect is likely to be. And that will allow you to triage a lot of methods out, which you wouldn't have been able to before. And a lot of that will depend on computer modeling. And so that's very important. And the other area is reduction, which is that we should not use any more animals than we absolutely have to. But I should also add, we should make sure we use enough animals so we get a proper result. Otherwise, you're wasting that resource. And this is the shameless plug for Rosemary, who's sitting there, who knows all about, in fact, everything. One of the world's leading authorities on experimental design. And a crucial component of reduction is proper statistical experimental design. And experimental design, which I won't talk about in detail, is a mathematical technique which ensures that when you do an experiment, you do it as efficiently as possible. And there are a lot of very clever ideas about ways of testing lots of different effects simultaneously and getting the most information you can out of expensive and valuable experiments. And animals are particularly valuable because, in a sense, they have no financial, I mean, apart from being expensive, they also have an ethical value, which is that you should not use more animals in experiments than you need. And then when you've done your experiment, you can go out to dinner and eat meat which has been produced in ways, or drink milk for that matter, if you're vegetarian, which is produced in ways which I would never give a license to at all. You can do virtually anything to a farm animal you like, or a chicken, but you can't if we're giving you a license to do so. And so part of my work is to encourage the use of proper experimental design among people who are performing animal experiments. And I would like any statisticians present, it's not a kind of very fashionable area to work in, but it would be great if statisticians would take seriously their responsibility towards the animal experimentation community to help them with their experimental design. Now, I'm going to change gear a bit and talk about the work of the Centre of Applied Science and Technology, but this is where I work. This is the Home Office, and I work just round the corner, just there, and I work in this building. And inside it just looks like a lot of open plan offices. And anyone who has spent any of their life trying to persuade an Oxford Don to have room X rather than room Y will know the attraction of working in a room where everybody has the same desk in the same space. Sorry about that. Now what I want you to look at here is not the building, but it's the bollards. So it's, I don't have a pointer, but it's these bollards here round. And you will have noticed that there are bollards like that round many buildings in London. Maybe you haven't, but there are. And they're a distance away from the building. They're not ordinary bollards. And that's not a secret, because if you were around in Whitehall in 2008, you will remember that the whole place was being dug up. And if you saw what they were installing in the trenches, you can't actually have secret designs of these things because someone can watch them being installed. So I haven't got any diagrams of what goes on, but I can tell you that the way they work is there a whole system where there's a sort of, the bollards are put into a concrete thing, and there are things sticking out horizontally. And the whole point, that's what it looks like now, and the whole point is that if you drive a car into it from this side, it won't fall over. So it's got things sticking out. And the whole design was designed and specified by one of the laboratories which are under my purview. That's why I put them there. And the other interesting thing is that they're rather nice because they don't look, unlike the protective security around the Houses of Parliament, which looks horrible because it has to be it's movable. That's why. These things actually are rather elegant. And you'll also notice further down Whitehall, it took me so long to get all these pictures off Google Maps, but probably illegal, that there are what appear to be stone blocks, and they are not. They're metal with cement concrete inside, and the reason is, of course, if something blew up against one of those, you don't want the block itself, you want it to absorb energy. And they're plastic dustbins. All over London, we have things which are very clever, which are there simply to minimize damage in the case of things like explosions and that sort of stuff. And the other thing, of course, one does is to make sure that the bollard is far enough away from the building so that you've got a standoff distance. And all that sort of stuff was thought about by Home Office laboratory. I don't think there was very much mathematics involved in that, but it's just to give you an idea of the sort of thing we do. Okay, now I want to talk about finite element analysis. Some of you will know what this is and others won't, so just give you an example of this. So one of the things we want to do is to protect buildings from explosions, and predicting how an explosion will affect a building allows us to design a safer building. A building is a complex object, so how do we actually model it? So there's a method called finite element analysis, which is a method of applied maths, and this is a way of simulating complex physical systems. What you do is you use physics, formulas from physics, but you combine those with an enormous amount of computer power, and those are the two things that you need. And the history of this goes back to the 40s, the 50s? Yes, that's right, but I think I understand it was a little bit earlier than that, so my research suggests it was the 40s. But anyway, it's the 1940s, and it was Zienkiewicz was the man who really, yeah, that's right, yes, so he was the man that really did it. But that was actually particularly in the physics world. What you do is you break the structure down to a large number of small elements. Time is also broken down little steps, and the effect of each element on its neighbours is worked out. And it's complex because it's both space and time. It was absolutely prophetic to have thought all this up in the days before there was heavy computer power. And what's also interesting, not a Home Office issue, is that climate modelling works the same way. So the way climate modelling works is that you take the whole of the Earth's atmosphere, you've got and the sea and all this sort of thing, and then you break it up into layers and pieces and so on and so on, and you then run time for years and years and years, and you've got equations that explain what goes on, and that's how climate models actually work. And that's why you need such enormous computers. The hunger for computer power with finite element analysis is enormous. And I'll just show you how it works in one case that we've got. So we're going to show you, I'll show you a video of modelling a bullet hitting a piece of glass. And the elements of the glass are different sizes, and I'll show you in a minute. And near where the bullet hits, the piece are tiny, far away they're large. And the other thing we do is that if an element is damaged in the equation, then it's destroyed. So let's have a look at where we are with it. So I hope this will work. Well, before I fire the bullet, let me just show you something. So the little pieces that you work out the physical equations, if you see over here, they're very small. And then when you get a long way away from where the bullet's going to hit, you make the boundaries larger and larger and larger. And similarly in this direction. And so round here, an element is just a tiny little cube. And the way it has to work is that over here the element is long and thin, and over here it's a flat piece. I don't know enough about this example. If it's done sensibly, it's possible that these are thicker as well, but I'm not sure how easy that would be to do. That's a little clever trick that helps you if all the action's going on in one place. If the action's going on everywhere, as is in climate modelling, it doesn't help you very much, except I don't know enough technically about it, but I guess if you were interested in the climate in a very small place, you might have larger elements further away. But just finally on climate, you know the joke that in this country, and it's particularly true at the moment, there is no climate, only weather. And believe this year seems to be particularly so. In other words, it's all statistical variability, and there is no underlying signal at all. That's not true, unfortunately. There is undoubted climate change. Yes, sorry, I can't remember. Good joke. Anyway, I can't remember the context. And the bullet itself has also got little elements in it. So we've got brass on the outside and lead there. And the way it will be modelled is that the physical equations will be different for the glass and for the lead and for the brass because they all behave differently under pressure and that sort of thing. So there we are, and you can see this is a computer model of what happens when the bullet goes to glass. You can see the bullet deforming as well. So there's an example. Okay, so this approach can be used to model all sorts of things: wind on skyscrapers, the effect of dropping an electronic device. So if you wanted to produce an electronic device that was very, very robust, you would use a finite element analysis on the design that you had produced. There might be applications where you would want to do that. It can do how an earthquake affects a building, how explosion affects a structure, and climate. And in fact, any physical system at all that involves components, and that's all sorts of things. So it's a very, very widely thing. So we're going to show the effect of a blast on a simple structure. And there's a little interesting trick. So we'll start by thinking about inside the structure. And what we do is we break up the space into small units and let the blast move. So here's the, now what I want you to imagine is there's going to be a blast, blow up in a minute, but imagine that the outside of the structure is fixed. So this is what happens. So there we are. So you get an explosion and then waves go backwards and forwards. For the sophisticated members of the audience, the numbers on the left show that the range of the colour scale is getting smaller as we go through time. So in other words, the difference between red and blue is much smaller at the end than it is at the beginning, pretty obviously. But what it does show is the way that and this is very important in an explosion because it will show where the positions of high pressure are. I'll just do it one more time. So it'll show where the red points are. That's where there's particularly high pressure, which is likely to do most damage. And that's why this sort of work is quite important if there's going to be a blast. Right, so now we're going to model the effect of the blast on the light parts of the building. So this time, instead of breaking the space in the building up, if the building is 3 dimensions, you might think we're just looking at the walls and the roof. And walls have bricks in, and they are themselves finite elements. So you can actually model bricks in walls as being the individual elements, and that's what is done. And so let's see where we are with it. So here is the next example. So what happens is you've got the bricks, the doors, and the roof. And here it goes. So the pressure eventually forces those out, and that's what happens. And so the light parts blow off and so on. So one way of making a building that won't fall down is to make the roof so that it can blow off. But the problem with that is that you have a roof blowing off, but it may be better than having the other thing. And now, so the light parts of the building are removed from the modelling once they're detached from the structure. So once the doors have gone, they've gone. And to find out what happens to them, we can model the bricks as elements, and then the physics is gravity and the effect of the pressure of the blast, and you can see what goes on with that. So that's what happens to the walls. And so what's interesting is you can combine the different parts of the modelling. You cut up the air inside the building into lots of little cubes, but the walls, you don't have to do that because they're essentially 2-dimensional, and you can just model those as individual bits. And of course, you get the idea of how far the damage is likely to go. Well, that was very interesting. And now for something more interesting, which is, I'm afraid the pictures I'm going to show are not that wonderful. But yes, we do blow real things up. Trains, buildings, etc., etc. We don't do it on our own premises, but the Home Office has done work on things like the effect of blast on trains and on buildings, and it's obviously very important, unfortunately. And so this is not a very good video. Unfortunately, the chap that did this for me went on paternity leave and said, I've left you all the stuff, and then when I got to look at it. But this is actually a real video, but I've looked at it several times and I can't actually understand it, but it is actually a real experiment we did, and you can see, that's right, you can see the walls and then the blast blowing it out and so on. So this is a real explosion that we did. Of course, it shows you nothing that you couldn't have got from just mathematics. Right, now, let's see where we are. Now I'm going to go back from something invented in the 1940s to something invented in the minus something or others, about 200 BC, Archimedes and now. So, we're interested in locating a radio transmitter. And why? Well, it could help us to protect vulnerable people and VIPs. It could help us to keep track of offenders and property, and to undertake search and rescue operations. There's various different contexts. Of course, I mean, I should explain this work is a little old, and there's GPS now, but GPS is not that accurate, and not every item is amenable to GPS. So I just want to say that. We don't always have control of the transmitter, so how can we find it? So if someone has a radio, how can we actually find that? So I'm going to talk about conic sections. Now, many of you will know this. To those, you can think about something else. But those that don't, this is, interestingly, conic sections are things that probably younger people don't think about at all. Those of us that were educated some time ago learned all about them, but I imagine a lot of young people don't. So if you take a cone and you cut through it, you get a circle, a little green circle. But another way of thinking about a circle is, actually there's something wrong with the aspect ratio here. A circle is all the points which are the same distance from the centre. And so the blue line length as you go around the circle is constant. So as you go around the circle, that's what you get. Now, if you cut the cone at an angle, you get an ellipse. The picture is not very good, I'm sorry. Those 2 points, those foci should be more like there and there, but never mind. And an ellipse has the property, and as many of you will know, that the sum of the two lengths is the same. And when I was a kid trying to draw one by having a piece of string, 2 pins and a pencil, and as the pencil went round, it gave an ellipse, except I'm not very good at physical things, so it didn't always quite work. But that was the idea. Easy to write down all the coordinate geometry, isn't it? And so what happens as you go around the ellipse is the sum of the two lengths is constant. So if we do that, it does that. And now there's also a thing called a hyperbola, which is what you get when you cut a cone that way, and you get a curve like that green curve there. And that has the property that the difference of the two blue lines is fixed. So that distance minus that distance is the same. And so if you do that, it does that. So that's some, as I say, I won't take a... I hope someone in the audience didn't know that already. If you all did, never mind. It's nice to know it again. So now let's imagine the way we find things. So let's suppose that we're trying to find them. That's a good way of thinking about life, isn't it? So, or maybe they're trying to find us. But anyway, we're us, and we're trying to find them, whoever they are. And they can receive and transmit, and so can we. So what we do is we transmit a trigger signal, they reply immediately, we receive a reply, and we measure that distance. So we know how far away they are. We don't know which direction, we know how far away they are. Radar works like that without transmission. It works just by reflection. But of course, the amount of signal you get back is not very great. So I want to presume that you get an actual signal coming back. Right. So that's we can calculate the distance. So let me see how this works. So there's us, there's them. So we know where they are, and the point is that they are somewhere on the circle. And then, I'm not quite sure what's good. So basically, if we are us, we can always find out which of these blue circles they are on. So they're on the green circle, but if they're nearer, they'll be on one of the inner circles and so on. Now, imagine there's one of us. We send and receive, and we discover that they are on the green circle. And then there's another of us, two of us. So I have one of my colleagues over here, and she or he finds out that the individual or the transmitter or the object is on the blue circle. And then we have the third one. So there's three of us, and they're on the purple circle, so they must be there. And so they must be at that point on the intersection. Now, notice that what do we need here? They have to have a transmitter-receiver, And we need 3 transmitter receivers, one to do that, one to do that, one to do that. And each one has to do a ping and get a ping back. And so you need 6 transmissions to get a fix. And the other thing is, of course, if they don't all happen at the same time, this thing may have moved around. So you have to also coordinate where you are. 6 transmissions, and you have to coordinate, and they have to hear you and you hear them. Now, there's a thing called multi-receiver radar, which works rather differently, which is where all I do is transmit, and you have a receiver. English language is good, isn't it? 3 different persons. So I transmit, they hear it, transmit, and you receive. Okay? You receive a signal somewhere else, and you measure total flight time, calculate total distance. I mean, you might call this friendly reconnaissance, because imagine they actually don't mind you knowing where they are, and you just want to know. Now, interestingly, what we measure is the total distance from me to them to you, and that makes us think about ellipses, and that's indeed what you get. So if they're there, you know that they're on that ellipse. That's an ellipse because we know the total time it took to get from here to there to there. Now this is interesting because imagine if I had another receiver but the same transmitter. The sum of the distance is known, yeah? And therefore they're somewhere on the ellipse. And so you know if I'm here and you're there, we can pin someone down to be on one of these ellipses, and in this case the green one. Now, so let's suppose that's our transmitter. So that's me, and I have a transmitter and receiver, so I know they're on the green circle. But I also have another receiver over here, just a receiver, and that receiver, with that, I can find out that the individual thing is on the blue ellipse. And then I can have another receiver, and then I get another ellipse. And obviously that means that what you're looking for is there. And so the point is that they need a receiver and transmitter. We still need 3 receivers, but there's only one transmitter, and there's only one transmission from me, and there's only one transmission from them. So it's a single ping, but you can pick it up in 3 different places and then get ellipses. And so that's a lot better for various obvious reasons. And then I'm finally going to talk about what you do if you want to find a transmitter where you don't want to transmit anything. We can receive in 2 places, they can transmit, they transmit, and we measure the time of reception in 2 places and the difference. And then you use a hyperbola. And we measure the time of reception in 2 places, we calculate time difference arrival, and that gives us a hyperbola. And so, and so we know that they're somewhere on the hyperbola. And then you have another transmitter, another receiver. So that's one pair, you know they're on the green hyperbola. You have another pair, you know they're on the blue hyperbola, and immediately by using this pair, you get a 3rd hyperbola, which looks like that. And I have a horrible feeling, and someone who's better at maths than I am will tell me whether it also meets over there. That's for Chris Budd to think about. He'll tell you whether it gives it to you uniquely, but that's not the point. The point is that you know you think the person's there. So they transmit at random. We have 3 receivers. We don't need any transmitters at all. All we need to be able to do is discern the difference. And we can do it silently, and there's only one transmission. So what's fun, I think, about this, again, if you didn't know about conic sections before, you do now. But even if you did, it's a way you can explain to other people why conic sections actually have an application nowadays, 2,500 years after they were originally come up with. Monte Carlo modelling. The last thing I want to talk about is Monte Carlo modelling. Our operational researchers use Monte Carlo modelling even as I speak in many different contexts. So Monte Carlo modelling is basically, as many of you will know, calculating many real systems work randomly, and you basically generate random numbers and then you put them into the system and you can figure out how the system will actually operate. Of course, often, if you take queuing theory as an example, you can predict mathematically things about the queue without doing all the Monte Carlo modelling. But the advantage of Monte Carlo modelling is that you can predict quite complex systems to see how they will actually work. So Monte Carlo modelling is very important, and this can involve both human behaviour and physical systems, and in the Home Office we do both. And the last example I'm going to give very briefly is one of these. So there's a thing called Program Cyclamen. This is off a website. It's a key part of the government's counter-terrorism strategies. It's cut and paste from a website. It involves a screening of incoming freight, vehicles, passengers and pedestrians to detect and deter illicit importation of radioactive and nuclear material by, well, actually I shouldn't say by terrorists or criminals, by anybody. Because if you importing illicit importation of radioactive nuclear materials is not an activity that is legal, so it's illicit. So therefore, please don't do it. And you're not. So yes, that's right. So the website didn't need to have those words in, but there you are. And if there is fixed radiation detection equipment at ports and airports, and there's a mobile capability supporting fixed portals to keep us safe by ensuring that air, sea, channel, tunnel traffic entering the UK is subject to screening. So this is all public information. And as is everything I'm going to talk about. But what I want to say is that there's a problem because if you bring in a lorry load of bananas or of ceramic tiles, that gives out a lot of radiation. So simply measuring whether something gives out radiation is not enough to discover whether it's... So, I suppose bananas are not illicit radioactive material. They're licit radioactive material. And so are ceramic tiles and lumps of granite and that sort of stuff. So, one of the important things in the design of all this, and I don't want to go into much detail, radioactive decay is random, and it's difficult to predict what escapes from a hidden source. And how do we model it? And the question is, how do we distinguish a lorry load of bananas or ceramic tiles from one containing illicit radioactive material? And the difference is, of course, that bananas actually, because they have potassium in, do actually have quite a lot of... And, there's all these stories about the nuclear, about, how many bananas would you have to eat to get the same dose of radiation as you did by living in Tokyo during the Fukushima event. Probably about 1 or 2 or something. I don't know what the answer is. And certainly getting an aeroplane, as you know, exposes you to a lot of radiation, as does living in Cornwall. So don't live in Cornwall. Illicit radioactive material comes in small pieces. So that's the difference, really, that an illicit that's really the point. So how do you model it? Atoms emit radiation, and they emit it in a random time, random direction. The radiation can hit another atom, change direction, trigger another emission, and so on, so on. Difficult to calculate probabilities for a chain of events. I'm not going to show you a test of this sort. We're only going to do the mathematics. But you can use a random simulation model to repeat possible outcomes thousands of times to build up the overall pattern. So a natural radioactive source is spread in general all over the cargo. So to get a reasonable amount of radiation, you need a lot of bananas. And so this is a schematic of the detectors and a container or something like that. A threat is probably a single item in a load, and of course one's looking for quite small quantities. And simulation can distinguish the different patterns that each scenario presents, and this is some work that was done at some time to look at that. Okay, well, that's a tour through a lot of different things. I hope it's given you a flavour of the sorts of things that we do. I'm very happy if people want to ask any questions, either about this or anything else that I might be doing. And I hope what I found really interesting going into government, I've been in my job about 2 years, is the enormous breadth and the way in which you might be asked a question 1 minute about any of the topics that I've talked about, and all sorts of others. And there's lots of stuff I do which is biological content as well. And you just have to be able to essentially know enough about it or know where to find out in order to make sure that the people that make decisions for us make them right, that they have the best information they can about it. And what interests me is just how fascinatingly different how varied it is, how exciting it is, and it's a great privilege to be able to help in this way. And I hope that I've managed to share with you something of the flavour of what we do in the Home Office, in our scientific work. So thank you very much indeed. Thank you.
For all information, please visit www.gresham.ac.uk.